Florida, orphaned from Africa, assaulted by the Appalachians, and forcefully clashed with Cuba, and home to the land of sinkholes. I'm Helena Aves, a geologist and historian. I would like to introduce you to the amazing geological history of the state of Florida, which is now my home. The story is a bit complex, but I will try to introduce you to the subject at an easy pace so that all who wish to know about the subject will be able to understand the general geological history of Florida. Welcome to Florida, the Sunshine State. As I have personally found out, Florida is old. It has been advertised to be a lovely place to call home. This is a map of Florida. I've been living here for the past 8 years, and as many, I wish I had come earlier. The map I am showing you is the topographic map of Florida. A topographic map is a detailed map that shows the elevation and shape of the land using contour lines. These lines indicate different heights, helping to represent hills, valleys, and flat areas on a flat surface. The elevations are shown in color variations, with the highest elevations showing as dark blue and purple, and the lower elevations are shown in a dark red to orange. Those lower elevations are between 0 and 10 meters above sea level, 10 meters being 32 feet above sea level. The maximum elevation is approximately 344 feet, or 105 meters, and it's located in the Panhandle, the northern portion of the state. Much of Florida is virtually flat, with only a few feet of relief and lying only a few feet above sea level. The geological past in Florida is mostly out of sight. Now let's look at the continental offshore shelf platform, or shelf area, off Florida. The continental shelf is the underwater area that extends from a continent's shoreline. It slopes gently away from the coast and can stretch for hundreds of miles before the ocean floor drops off sharply. This shelf is rich in marine life and natural resources because it's relatively shallow compared to the deep ocean, receiving plenty of sunlight and nutrients. As you can see from the dashed line, which represents shelf subsea depths of less than 200 meters or 656 feet. This is a very large, shallow water shelf platform that extends westward offshore Florida up to 200 miles. Here is a more detailed version of the Florida platform. This diagram shows a more detailed 3D representation of the Florida platform and the steeper slope regions, which were discussed in the previous slide. Consider it to be a huge flat plateau with shallow offshore water levels, sloping sides that eventually drop off into the deep water. As we will discuss a little later, the Florida platform itself is slightly sloping to the west. The Florida limestone platform is a large porous plateau made mostly of limestone. It sits atop bedrock and was formed about 176 million years ago when the area was submerged under a shallow ocean. Over time, layers of marine life, like shells and corals, accumulated and compressed into limestone. The diagram shown is one of a shallow marine limestone carbonate environment, as the Florida platform is. Within that platform, there are areas known as the inner shelf, the mid shelf, the deep shelf, and the upper slope. As you can see, depending on the water depth on the platform, will be conducive to various types of calcium carbonate species that will thrive in those areas. As you can see, in the 70-meter range, we have mollusks and red algae, and then slightly deeper water, we have bryozoans and benthic forams and so on. Just to show you that the different environments and water depths will induce various species to propagate in those areas. Florida limestone platform has been building up for the last 176 million years. To the left of the diagram, you will see the geological column, and it's showing you that the majority of the carbonate sediments that have been deposited, both onshore and offshore, are of Jurassic and younger age. As you can see from the diagram, about 5 kilometers of carbonate rocks have accumulated on the Florida platform during the 176 million year period, and about 12 kilometers of carbonate sediments in the offshore eastern trough. So what is limestone, you may ask? Well, limestone is what geologists refer to as a sedimentary rock. That is, it's composed mainly of seashells and organic carbonate material. It is also a compound of calcium carbonate. The primary compounds from seawater that form calcium carbonate are calcium ions and carbonate ions. These ions come together to precipitate calcium carbonate, which is a major component of marine sediments, shells, and corals. These compounds are used by marine organisms to create their shells. Most grains in limestone are skeletal fragments of marine organisms such as coral or foraminifera. Foraminifera are very small, single-celled organisms that contain shells. These organisms secrete shells made of aragonite, a form of calcite, or calcite itself, and leave these shells behind when they die, and virtually accumulate into large calcium carbonate platforms. Let's look at some types of limestones. In the upper diagram, we have a limestone known as coquina, which is a poorly cemented limestone that is composed mainly of broken shell debris. In the middle, we have an example of fossiliferous limestone that is composed of mainly large fossils, as you can see in the picture. And finally, on the other extreme end of the spectrum, we have what is known as chalk, which is extremely fine-grained material of calcareous carbonate composition. Chalk is composed of shells of minute marine organisms such as foraminifera, coccoliths, and rhabdoliths. The purest varieties of chalk contain up to 99% calcium carbonate in the form of the mineral calcite. The White Cliffs of Dover pictured in the slide is an excellent example of chalk formations. How does the limestone platform form? Well, as we discussed slightly earlier, the primary source of the calcite in limestone is mostly commonly marine organisms that have a calcium carbonate composition. As they die, these accumulate as deposits of calcium carbonate on a flat-lying platform sub-sea level. Some of these organisms can construct mounds of rock known as reefs and build up over generations and create coral reefal structures. The animation to the right of the diagram indicates how a limestone platform can build up over time. The Florida platform is a carbonate platform that extends well offshore to the base of the continental slope to the east. To the south, to the base of the West Florida Escarpment to the west, the Florida platform was once part of a much larger Florida-Bahamas platform in the geological past. The thickness of the Florida platform varies depending on whether you're in the onshore portion or the western portion or the eastern portion. As an example, onshore, the limestone thickness is approximately 2 to 3 miles, and it lies on top of an old basement. And to the west, it's considerably thicker. It goes down to 5 miles. And the eastern portion, the thickest portion, is approximately 10 miles. And it's the downdrop portion of the older Bahamas platform. The graphic shows the early Florida-Bahamas platform and its enormous extent. Eventually, by the Middle Jurassic, or about 164 to 174 million years ago, a thick succession of carbonate rocks produced one of the largest carbonate platform complexes ever seen on Earth. This is what the Florida-Bahamas platform looked like before the tectonic forces broke the platform in two, caused by the collision of Cuba against the Florida platform, which will be discussed shortly. The sea level during the last glacial maximum, approximately 26,000 years before present, has changed dramatically. As you can see, the dotted red line indicates the location of the sea level during that last glacial maximum. Sea level was close to the edge of the carbonate platform. Since that period, 26,000 years ago, sea level has risen about 400 feet. The record of any civilizations that may have existed in the lower platform area during this period is clearly now underwater. The platform reaches its maximum extent at around 100 to 150 miles from the current coast, specifically in the area of the Florida Keys in the southern part of the state. Let's look at how Florida formed. Let's go back in geological time about 400 million years ago. At that point in time, there was a huge landmass which encompassed all of the continents that we have today into one large mass, which is known as Pangaea. This slide shows what Pangaea looked like about 300 million years ago. And look specifically in the expanded version to the right, the location of Florida, which was actually part of the African continent before Pangaea broke apart. The arrow will indicate that location quite clearly. In fact, Florida has now been determined to have been part of the African continent before it broke apart. In particular, it has a Senegal connection, as you can see on the graphics supporting this conclusion. There are similar rock types and basements that have been found both in Florida as well as Senegal, which clearly identifies the origin of Florida as being part initially of the continent of Africa. It was breaking apart. Florida remained attached to the North American plate after the breakup. This animation shows the breakup of Pangaea in 4 phases over a period of about 175 million years, during which time the Atlantic Ocean and the Caribbean Sea were formed. This is a squinties animation of the breakup of Pangaea. It is extremely updated and the most accurate that we have to date. Pay close attention to the area within the circle, which is the area where Florida starts to break apart, and the beginning of the breakup of Pangaea that is occurring between the North American plate and the African plate. It's happening about 175 million years ago. The second thing to look for in the animation is the portion which now we understand as being Cuba and its collision with the Florida platform at approximately 50 million years. And then finally, the formation of the Caribbean plate as we know it today. This diagram shows the progression of the formation of the Caribbean plate. From 84 million years to 36 million years, critical points at which the Caribbean plate was forming. To the left, at 84 million years, you can see the Florida-Bahama platform, and it's still intact. And also of great interest is the location of the Greater Antilles Island arc chain that is moving at that period of time in a northeasterly direction towards the Florida-Bahama platform. At 72 million years, you can see that the continuation of the northeasterly projection of the Greater Antilles Island arc chain getting closer to the Florida-Bahama platform. At about 59 million years, you can see that Cuba actually collides with the Florida platform, Cuba making up the Greater Antilles and its collision with the Florida platform, which we will discuss in a little more detail later. And also of note is the future Isthmus of Panama and its location. It is also moving in a northeasterly direction and will eventually form the Isthmus of Panama by the 36 million year old mark. And the last panel at 36 million years before present shows that the Florida-Bahama platform will have been separated. And then the Cuba, in fact, the tectonic boundary of the Caribbean plate is actually to the south of Cuba. Cuba is no longer in a tectonic zone. It is no longer part of the Caribbean plate. And in fact, the entire Caribbean plate at this point in time is moving to the northeast. And then, of course, the final thing to note is that the Isthmus of Panama is also beginning to form. As it has been explained earlier, and the Florida-Bahama platform broke up as a result of this crash with Cuba. In addition to that, it also formed the Straits of Florida where the breakage occurred, as shown in the diagram. As a result of the collision of the Florida platform by Cuba, we also have two other things, as was mentioned earlier. First was the formation of the Straits of Florida, which delineate the two portions of the previous Bahamas and Florida platform. The collision of Cuba with the platform, carbonate platform, also created a sloping effect in which the entire continental shelf of Florida now slopes to the west at an average angle of about 3 degrees, but it can be as low as 1 degree or as high as 10 degrees. And this was a direct result of the collision of Cuba and the carbonate platform. The results of the crash at Cuba approximately 59 million years ago with the Florida carbonate platform is shown in the diagram. The hatched areas shown to the north of Cuba indicate the locations of the carbonate platform that was uplifted onto the Cuban plate during that collision. And this can be seen on shore, as you will see in a minute. The tectonic forces that crushed Cuba into the Florida platform resulted not only in that collision, but also allowing the thrusting of the Florida platform on top of the northern portion of Cuba. The Cuba collision caused the uplift of carbonate sediments of the Florida platform to buckle and uplift along the northern margins of Cuba. These features are called mogotes. The photograph indicates the location of the mogotes, and you can clearly see that they are uplifted. They are carbonates, and these features are very characteristic of the northern portion of Cuba. Go to part 2 of this presentation, which will discuss the Florida Everglades and the Florida Keys. They were formed through unique geological processes over millions of years. The Everglades developed as a vast wetland, while the Keys originated from ancient coral reefs. Today, these areas face environmental challenges like wastewater management and mining pollution, as well as urban development, making conservation efforts crucial to their preservation.